Uh, Good afternoon, everyone. I want to welcome you to another start class. You know, what we want to do today is very, very important, and I need you to pay attention. Of course, I've graded your report, and I left some messages, and we advise that you take note of the post already comment, but I'm actually going to have a wrap up on the on consulting. Let me just say the reason why some didn't get 100% is because the final model they arrive at, they did not investigate whether assumptions hold. In any statistical model, there's always going to be assumptions. Okay. So, and even though you've done all what you are supposed to do, and you arrive at a final model, okay, you need to be able to investigate whether assumptions underlying the use of the model hold, because what make a model to be fantastic is when assumptions hold. Does that make sense? So because of that, I'm actually going to have a wrap up on that. And I also realize, some student, maybe one or two, actually use an inappropriate model. When you are talking about repeated measure, you don't use all a model that is entirely fixed effect. Okay? Even though the fixed effect model you actually use turn out to be significant, the fact that you are using a wrong model, okay, does not, even if it is significant, does not make it right. I told you the other time that somebody commit an offense in a state and run to another state, even if the court in another state establish the fact that that guy commit the offense, whatever their decision is going to be declared non and void, break their law. And one or two students did not understand what we mean by statistical report. And that is the reason why you need to look at the rubrics. Statistical report actually means you've looked at the objective, you've analyzed the data using appropriate statistical methodology, then you investigate whether assumption hold. Situation where assumptions are violated, of course, there's always going to be a way out. So what I'm going to do today, I'm actually going to, tell you and show you what we need to do, okay, whenever we are analyzing a repeated measure. Okay, the data you have from Adam is a longitudinal data. Okay, now I need you to pay attention. Like I said, when you have a repeated measure, you cannot use fixed effect model. Does that make sense? It's always going to be a mixed effect. You're always going to use a mixed effect model. The mixed effect can be linear. We could have a linear. We could have non-linear. Okay. We could have linear mixed effect. We could have non-linear mixed effect. Okay. Now, when you're talking about linear mixed effect, okay, we got y equal beta naught plus beta j beta 1 sj. Okay, if you only apply this, whether in a simple linear form or in a multiple linear form, you are actually using a fixed effect. A fixed effect is not good for longitudinal data. Longitudinal data where there's a repeated measurement. What do I need to do? Then I'm actually going to I can incorporate a random intercept, also incorporate a random slope. This is a random intercept. This is a random slope. And the last thing, there's going to be a final error on the module that is always EIJ. This is a linear mix effect module where this side is fixed and this is the random part. Okay, there are two random parts. The random that you created, okay, assuming the random intercept and the random slope, and there's always going to be, in any statistical model, there's always going to be a residual. There's always going to be error. Okay, this is a conventional one. Now, and if you take a look at what I have here now, so if this is a Yij, so the Yij, if I want to rewrite this, I'm actually going to have, okay, this plus, I'm actually going to have B1 plus Bi2Sj plus Eij, where this is a combination of the intercept, both fixed and random. And this is a combination of the slope, both fixed and random. And this is the error part, the random part, the conventional error in the model. Now, if you want to fit this model to your data, we got assumptions. Okay, we got assumptions. I want to talk about assumptions underline the use of a mixed effect, linear mixed effect model. I want you to take a look at what I mean by linear. Linear, it means relationship between your response variable and the independent variable. That relationship is constant, which is a linear one. Okay, and how are you going to investigate that linearity? Then you can actually use a diagnostic plot like a residual plot. Has anybody heard about residual plot? You know, we got some diagnostic plots. Okay, one of the diagnostic plots is residual. Okay, residual plots. Okay, you talk about Q plots and so on like that. Now, when the residual plots show pattern, okay, when there's a pattern in the residual plot, then it means assumptions of linearity is violated. But if the residual plot does not show pattern, then it means the linearity assumption holds. But what if in a situation where linearity assumption is violated in a linear mixed effect model? What am I going to do? Then I will have to think of either transforming, you've done all of this before. This course is different from a traditional course. We are actually building on the fact that you've offered some courses coming into consulting and communication in statistics. We're building on that knowledge you've acquired. Okay, now what I'm trying to say now, situation where linear relationship does not exist, we can think of transformation. It's either we transform Y or we transform the independent variable. You can talk about square root transformation. You can talk about, a log transformation. You can talk about Bosco transformation. Has anybody heard about Bosco transformation? Because of the fact that the whatever module we want to use in statistics, okay, as assumption, and if the assumptions are violated, we can never trust whatever that will come out from such module. Okay, now I've just told you now assumptions of linearity, because this is a linear mixed effect module. Then another assumption that we actually going to have, okay, another assumptions that we're actually going to have, we target the fact that we got a random intercept, a random slope. Anything random is actually going to assume to follow a probability distribution. And do you know the probability distribution we are assuming now is actually, we're trying to say random intercept should follow normal, okay, with a mean of 0, and there's going to be a variance for that, okay? Then the random slope also follow normal distribution, okay, with the variance of that, okay? Then what about the conventional error in the model? The conventional error in the model follow normal distribution, okay, with the mean of this and sigma square, okay? Now, when you want to test absorption in your final model, okay, let me just say B2 and B1, because that occurs across I is observational unit. Maybe in the Adams case, the ID. Okay, now you after arriving at your final model, you need to investigate whether the distribution of the intercept is normal. You need to investigate whether the distribution of the slope is normal. You need to investigate whether error follow normal distribution with a mean of 0 and a constant variance. Okay, and if you really want to do this, I can use a QQ plot. Okay, or you use the histogram. Okay, of like if I use the histogram of residual, I'll be able to know whether error follow normal distribution. But what of in a situation where there's a violations of normality assumption? What are we going to use? Then we can resolve into a non-parametric, okay, non-parametric test, okay? And one of the non-parametric tests is actually going to be either generalized. We got generalized additive model, or we talk about bootstrapping. Has anybody heard about bootstrapping? You should have, I think you're supposed to have done like bootstrapping in 4051. Applied statistics, that is bootstrapping, okay? That is bootstrapping, okay? So these are non-parametric way of seeking redress when there's a violations of normality assumption. Or we can use a robust method that will not assume normal, depending on the nature of data. Okay, I can actually use a robust method like assuming the underlying distribution follow Laplace, or follow exponential distribution, or follow any other form of probability distribution different from normality. Okay, but I have to put into consideration the distribution of the response variable before I'm actually going to come out with what the error structure is going to be. Let me tell you this. The distribution of Y, response variable, is always distribution of the error. Is there any question before moving forward? Now, what is another assumptions that we can actually talk about? We can talk about assumptions of sphericity. Okay, assumptions of sphericity. Okay, we're still under assumptions. Okay, sphericity. Okay, the sphericity assumptions actually saying the variance of the differences, okay, between any two pairs of repeated measure is the same over time. And I think we actually have a way to investigate that, because if this is not true, okay, you actually go to mislead. Type 1 error rate will be exceeded. Okay, what makes statistical model to be so I have some tests of sphericity that we actually call Macley test. in literature. You can check Markley test of sphericity to be able to see whether the sphericity assumption hold. The quality of variances of difference between all pairs of repeated measurements, we normally assume that it's going to be the same. What if it is not? If it is not the same, we cannot trust the model. So if it is not the same, what can we do? Then we got some corrective measure. Okay, corrective measure. We can decide to use what I call, there's something I call greenhouse Giza adjustment. Greenhouse Giza adjustment. Whenever there's a problem in statistics, there's always going to be a way out, but it is very dangerous when you ignore a violation. Ignoring a violation, your model, whatever recommendation that comes from your model, will never stand the test of time. So don't forget that we acknowledge from day one that there's always going to be a distance between our model and reality. And what makes our model to be great is when we are able to investigate all assumptions in a model. And all assumptions in a model revolve the error time. But let me tell you this. The random part of a model is actually called the unobserved. That is the random part in the model. Whether random intercept or random slope, they all belong to the random part in the model that we actually need to account for, in a situation where we don't want to mislead. Okay, which other assumptions do we have? We also have, like for instance, if your best model is a model with the intercept and slope, with a random intercept and random slope. I'm going to say that again. If your best model is a model, that puts into consideration the random intercept and the random slope, then we have another assumption. Okay, do you know that assumption? There shouldn't be correlation between a random intercept and random slope. What do I mean by that? When there's a correlation between a random intercept and random slope, it actually means a particular group, okay, that have a higher value of intercept, okay, we also have a very higher value for slope or lower value for slope. That is not, it's not going to be okay. But how am I going to know, whether the two variables are, the two random effects are correlated? Of course, I actually give you a test the other time to decide between uncorrelated and the correlated. But do you know the one that we're not going to have any issue? Uncorrelated. But what if in a situation, and I remember I told you, when you are testing uncorrelated against the correlated in the null hypothesis, you're actually going to have the two effects and uncorrelated in the alternative. The two effects are correlated, and if your p-value, you're going to use what I call a nested ANOVA test. If your p-value is less than any reasonable level of statistical significance, you're actually going to reject the null hypothesis. Rejecting the null hypothesis, you are actually concluding that your random intercept and the random slope correlate. But when they correlate, that's not good. Do you know what we now need to do? When the two correlate, then we need to be able to use a different covariance structure. That was why I gave you that material on the mixed effect model in R. There are three types of covariance structure. And what I want to explain to you now, what is the situation where we use a particular covariance structure? Okay, so there are three covariance structure in a mixed effect model. Okay, we got three covariance structure that we call covariance matrix structure. Okay, we call that covariance matrix, covariance matrix. Okay, number one. We have compound symmetric. We have compound symmetric. Okay, we got AR, which we call the autoregressive, and we got unstructured. You know what I need from you? What I need from you now is for you to be able to listen, ask questions where necessary. The question now, for me to be able to know which of these compound structure am I going to use, okay, then I need to be able to understand the nature of my data. Now, let me tell you, what is the meaning of a compound symmetric? The compound symmetric is actually believe that the correlation over time is the same. Correlation between any pairs of measurement within a subject over time stay the same. What if it does not stay the same? How am I going to know whether it's not going to stay the same? I can use a test of sphericity. Okay, if it stay the same, I'm going to use a compound symmetric covariance structure. Okay, the compound symmetric covariance structure actually believe that the correlation, okay, between pairs of measurement within a particular subject will remain constant over time. What about autoregressive? Autoregressive believe that changes over time. Okay, and that's actually believe that when the lag increases, for how many of you offer time series before? Anyone? Can I see your answer if you offer time series course in statistics? Okay, thank you. You've heard about autoregressive model, right? Where a model that relates the current with the past. That's what we mean, autoregressive. Okay, now the autoregressive covariance structure we leave when lag increases, the correlation goes down. The correlation decreases over time. I'm going to give you an example now. If you're trying to track recovery of patients over time, I'm going to say that again. In hospital, a physician is trying to track the recovery of patient over time. If you look at measures that are very close together, the correlation will be very high. But when you look at measures that are far apart, the correlation will be very small. In that situation, you use autoregressive covariance structure. When do I use unstructured? I'm actually going to use unstructured when I don't have the idea about the correlation. Then I'm going to allow the correlation to vary freely. Now, let me tell you this. Situation where random intercept and random slope correlate, okay? The best covariance structure to use is autoregressive. Because they correlate, then I'm going to use a covariance structure that allows correlation. You know, there's something in statistics. There should always be an agreement between a model and reality. When a model is, when reality is linear, then I'm expected to use a linear model. There's a conformity. When a model is non-linear, then I should use a non-linear model. In a situation where disagreement occurs between model and reality, then there is no way we can predict reality. And that is the reason why it looks as if our models are failing us. Our models are not failing us. But you know what? At times, as researchers, we always rush to take a decision. When you rush to take a decision, we are likely going to take a decision that we're going to regret. Imagine the waste of time, waste of resources. And that is the reason why we need to take it cool. We need to go through the process systematically. We need to do it, in a way, that is already laid out. I arrive at the final module. I need to investigate whether assumptions hold. There's another test that we can conduct whether correlation exists. I remember in time series, I can use my ACF autocorrelation function plot. I can also conduct a test of Dobby-Watson test in time series. To be able to choose the best model, to be able to write correct statistical reports. Correct statistical report indicates that you already understand the position of the client. You understand the position of the client in terms of the aim and objective of the study. You look at the objective of the study and you actually go into your statistical arsenal of weapons. I'm actually going to call it statistical arsenal. There's a lot of statistical modules. You play around statistical modules. You arrive at the final module. And after arriving at the final module, you investigate whether assumption holds. And if there's a violation of assumption, we're always going to have a way out. But if there's a violation of assumption and we pretend as if, it doesn't exist, then it's actually going to tell whatever recommendation we make will not see the light of the day. And you know what is going to happen? If we are consultants, that company is not going to visit us anymore. Because you actually make a recommendation that doesn't come to pass. Whatever you tell your client, they're actually going to wait and see whether your recommendation is going to come to pass. It's a matter of time whether it's going to come to pass or not. If it doesn't come to pass, it means you can't be trusted. If your model cannot be trusted, then you cannot be trusted. And that is the reason why we need to be able to do, put every necessary machinery in place, and we don't cut corner in statistics. Don't cut corner in statistics. Go the way it is programmed. Like, okay, after this, I'm going to do this. After that, I'm going to do that. Then when you have explored all possibility, you've already, conducted the test under a statistical procedure, then you can now authoritatively say, this is my conclusion. And that very conclusion is going to be binding anywhere in the world. Is there any question? For those of you who have written a report that actually have, a score that is not satisfactory, I think I'm going to give you another opportunity. If you actually put into consideration what I've said today, but it's not compulsory, you can have a resubmission and I'm going to grade it. Does that make sense? Do you hear what I just said, right? Like, I've graded already, right? You've seen your result. Okay. Now on this report, and if you feel that you want to improve on your score, okay, you can actually do all this and you resubmit, and I'm actually going to grade that. But you know what? If you're satisfied with what you have right now, that's okay. But the most important thing is you getting the right information. It doesn't matter whether you don't get it at the first time, second time. But when you finally get the information, then I'm fine. I'm okay. Is there any question? Is there any question? I think in the absence of question, okay. On Wednesday, I think I needed to check what is it called, the syllabus, and to be able to see, we got a panel coming up. Okay, I think maybe that's probably on Friday, but you can check where we're going to meet with alumni. Alumni, they're actually going to tell us how they are using the statistical knowledge in where they are. Okay, let me tell you this. Anywhere in the world, irrespective of where you work, the nature of work, whether you acquire statistical knowledge or not, you use statistics every day. You understand what I mean? Anywhere anywhere in the world, irrespective of what you do, whether you acquire statistical knowledge or you don't acquire statistical knowledge, you use knowledge of statistics every day. Because it has to do with numbers. And we because we live in a stochastic environment where there's a variation, because of the fact that different things happens in different days, there's variation. And as human beings or as companies or as individuals or as country, we actually want to make a prediction of the future. If everything is the same, there's nothing to worry about. Statistics thrives in variation. Without variation, there is no statistics, there is no mathematics, there is nothing to manipulate. Is there any question before I go? So this is what this is my lecture for today. And the last thing I'm going to say, let's say for instance, if you want to choose among these, let's say you actually run this, and this, and you now know you want to choose the one we have, the covariance selection criteria, like AIC and BIC, but somebody won Fitzmaurice won in 2011, we shouldn't use BIC, okay? Because you are likely going to select a model that is very, very simple. Situation, maybe the real life is complicated. The BIC may choose a very simple model. A simple model is not appropriate for a complicated reality. And that is why we can rely on AIC. The covariance matrix structure with the smallest AIC is actually going to be the best. Statistics is like a story that goes on and on and on. Even with my PhD, okay, I have not finished the story. The story still continues. But I do research every day, okay? So the story is not going to finish. Okay, make sure you all, if there's no any question, make sure you all stay safe and have a lovely day. Bye for now, everyone.